Thanks a lot for the kind introduction. I hope you can see my screen and hear me well.
Yes, yes.
And also thanks to all the organizers for inviting me. And it's really a great honor to have the chance to present my master project at this conference or this tutorial. So in a nutshell, what our project was about, it was about to accelerate Koopmans calculations in situations where we have to perform many Koopmans calculations on the same system, but with different atomic configurations. And this is, for example, necessary if you want to compute temperature renormalized spectral properties. And the approach that we took was to predict the screening parameters directly from the orbital densities instead of computing them ab initio. And here on the right, you can see a very typical setup where this machine learning model might be useful. So imagine you have generated a trajectory, for example, of this vortex system, and you wanted to perform Koopmans calculation on 20 of these snapshots. Then you could use our machine learning model in the following way. You could compute the screening parameters ab initio for the first couple of snapshots, so perform the standard Koopmans workflow as Edward was presenting to you in the previous presentation, and simultaneously use this data to train a machine learning model. And as soon as the model has seen enough data, you could use the trained machine learning model to predict the screening parameters for all the remaining snapshots, and thereby save a lot of computational time. So here you can see a very simplified version of the standard Koopmans workflow as Edward was presenting you in the previous presentation. And as he already said, the most expensive part of the Koopmans calculation, at least for large systems, is this part of the calculation where you have to perform, where you compute the screening parameters. So for example, you could use the delta SEF algorithm where you compute the screening parameters by matching these finite differences in total energies. But essentially this would require you to perform one DFT-like calculation for each orbital in the system. And this gets very expensive as you have many orbitals in the system. So instead, what we wanted to try is to predict the screening parameters directly from the orbital densities. And in the following, I will guide you through this process step by step. As you can see, the first step is identical to the first step in the standard Koopmans workflow. So you have to perform it in both cases. It starts with a standard DFT calculation to get the ground state density of the system. And as a second step, and this is also common to the standard Koopmans workflow, you would have to perform some kind of localization procedure to get a good initial guess for the variational orbitals. And as Edward was saying, these are normally very localized in space. And these are these quantities rho I from which we want to predict the screening parameters. And in practice, we use the Vanier orbitals. So now we want to map these orbital densities to the screening parameters. So in practice, one screening parameter is one scalar between 0 and 1, which corresponds to one orbital density. And to feed this information into the machine learning model, we first construct a very low-dimensional representation of these orbital densities. And we do so in 2 steps. And the first step consists of a local decomposition of the orbital densities into some radial basis functions and spherical harmonics. And what I mean by local decomposition is we center this integral around the center of the orbital, and we truncate this expansion after some finite value of Nmax and Lmax. So you can see this as approximating the true orbital density by some finite linear combination of these radial basis functions and spherical harmonics. And the idea is that this expansion should be most accurate in the direct vicinity of the orbital center and is getting more approximate as more you move out from the center. But as these orbital densities are quite localized for Koopmans, you can see that essentially already Nmax and Lmax equals to 6 are sufficient to accurately reconstruct the orbital density. So on the left, you can see the original orbital density, and on the right, you can see the reconstructed orbital density. For our machine learning model, we not only feed in the shape of the orbital itself, but also the total density, since the screening parameters will not only be influenced by the shape of the orbital, but also by the electronic environment of this orbital. And therefore, we perform the same kind of local decomposition as we did for the orbital densities, also for the total density. And here, because the total density is delocalized or spread out over the whole system, you can really see this effect of the local decomposition. So you can see that we are able to accurately reconstruct the total density in the direct vicinity of the orbital center, but of course we lose information the further we go out. Now we have constructed this vector, which consists of the expansion coefficients of the orbital density as well as the expansion coefficients for the total density. And in principle, we could now feed in this vector into a machine learning model. However, we wanted to make sure that our representation of the orbital densities satisfies some common invariances, namely invariance with respect to permuting the orbital indices, invariance with respect to translating the whole coordinate system, rotationally invariance, and also size invariance. If these invariances would not be satisfied by our descriptors, then the machine learning model would have to learn these invariances by themselves, and normally this requires more training data. Yesterday in Martin's talk, you saw an alternative approach, which was using equivariant neural networks. As you might see, the coefficient vectors are already invariant with respect to 1, 2, and 4, but they are not yet rotationally invariant. And what this simply means is that you get a different coefficient vector if you rotate the whole coordinate system. And this is not what we want, because we know that if we rotate the whole coordinate system, this corresponds to the same physical system, and it also will correspond to the same screening parameter. Probably the most simplest way to construct a rotationally invariant representation out of these coefficient vectors is to take this power spectrum. And you can show, so essentially you perform a scalar product with respect to the M indices here. And you can show that this is indeed rotationally invariant. However, if we would do this in a naive way, we would introduce some new problems. And one is that the indices corresponding to the orbital density and the ones corresponding to the total density are completely decoupled. So they are both rotationally invariant, but independent of each other. So, for example, you could rotate only the orbital density, but leave the total density here in orange unchanged, and this will lead to the same power spectrum. And this is not what we want, because here those two systems correspond really to different physical systems and will also correspond to different screening parameters. And a similar problem also exists for indices belonging to different n. And the solution that we took was to explicitly construct a larger power spectrum where we extend the power spectrum, the standard power spectrum shown here, by those terms where K1 is not equal to K2. So in this formulation, you always have the terms where K or this first k is equal to the second k, but we explicitly couple the values belonging to different k's by including those in our input vector. And the same story goes for different, to the coefficients belonging to different n. And this is now really the quantity that we take as the input vector for our machine learning model. For the machine learning model itself, we looked at different approaches, but what worked best in the end for our systems was simple ridge regression, where the goal is to find the optimal weights that minimize this regularized least square loss. And it is well known that this has a closed form solution given here. And as soon as the model has seen enough data to accurately compute this optimal weight matrix, you can perform or make the predictions via a simple scalar product of the optimal weight matrix with the new power spectra vector. So as I said, we have to make one prediction per orbital. So we have to map orbital 1 to the screening parameter 1, orbital 2 to the screening parameter 2, and so on. And after we have done so, we have the set of all screening parameters in our system. However, this is not the end of the story, because in the end, we are interested in physical properties, and for Koopmans, especially in spectral properties of the system. And to obtain these, we have to perform one final Koopmans calculation. And this is again standard, common to the standard Koopmans workflow. So also in the standard Koopmans workflow, you have to perform this final Koopmans calculation, where you essentially set up this Hamiltonian matrix defined now via the predicted screening parameters. And then the eigenvalues of this matrix are then the quantities that we take as approximations for quasi-particle energy. So those are then really the physical quantities that we are interested in. To test our system, to test our model, we considered two systems. The first is water, which is probably one of the most studied systems. And also here, quasi-particle energies are of great interest, for example, to describe redox reactions in aqueous systems. And the second system was this perovskite system, which is a promising candidate material for inexpensive and easy to manufacture next generation solar cells. And also when we talk about solar cell materials, really the quasi-particle energies and especially the band gaps are key figures of merit. So it's really interesting to study these materials with Koopmans functionals. Essentially, I have summarized all the results that I want to show you today in this slide. I will guide you through these results step by step. But let me first outline what you can see. So on the left, you can see all the results for the water system. And on the right, you can see all the results for this perovskite system. In the top row, you can see the results for a very simplistic baseline model that we just took to have some kind of comparison to see how much better our model performs if we introduce this more sophisticated approach versus just taking a very naive approach to predict the screening parameters. And then in the remaining rows, I show the results after an increasing number of training snapshots. So after increasing the number of training data, namely in the first row, I show the results after 1 training snapshot, then the results after 3 training snapshots, and then the results after 10 training snapshots. And each panel, again, consists of 2 figures. One is this parity plot, where I plot the ab initio computed screening parameters against the predicted screening parameters. And in the ideal case, all values would line up on this diagonal. And on the right, I show the error histogram here in blue of not the screening parameters, but of the physical properties, namely the quasi-particle energies. And when I talk about error here, I mean not compared to experiment or highly accurate quantum chemical methods, but compared to the quasi-particle energies that we obtain when we compute the screening parameters ab initio. What I also show is the cumulative error distribution, as well as the mean absolute error of the orbital energies and the valence band maximum, or the error of the valence band maximum and the error of the conduction band minimum. And so, as I said, this is a very simplistic baseline model. And we call it mean model because essentially we predict the screening parameters of the current snapshot just as the average of all the screening parameters of the previous snapshots. And we do so separately for the occupied orbitals and for the empty orbitals. Therefore, you get two flat lines. And you already see that this is a quite crude approximation because in reality, the screening parameters cover a wide range, or some range of values instead of only one value, which is common to all orbitals. And you can also see how this translates to the error in the predicted quasi-particle energies. You can see that it has a quite broad error distribution, and you get errors which are larger than 0.2 electron volts and many errors which are larger than 0.1 electron volt. And also the quantities that you're often interested in, namely VBM and also the mean absolute error, are really large in this case. So the goal of our model was really to outperform this model. Otherwise, we wouldn't have gained anything by using this more sophisticated machine learning approach. And this is indeed what we see. And what is really remarkable is that we see very good results already after one training snapshot. So already after very few training data, we see that all screening parameters essentially line up around this diagonal, and correspondingly also the error distribution of the orbital energies is very narrow. We don't have any orbital which has an error larger than 0.1 electron volt, and also the mean absolute error is quite small, around 0.02 electron volt, and also VBM and CBM are predicted quite accurately. I also want to draw the attention that this is a logarithmic scale, so most of the orbitals have an error in this range. So I would say for most applications, this accuracy might already be enough to get accurate predictions for the orbital energies. But of course, the results improve as you add more data to the training. For example, after 3 training snapshots, you can see that the error or the disparity plot is already much better than before, and also of course, the predictions for the orbital energies improve. And of course, the story continues as you add more and more training data. And essentially, after 10 training snapshots, you really see that all screening coefficients line up on this perfect diagonal. Now I come to the results of the perovskite system. So again, I start with this very simplistic baseline model. We get one prediction for all the occupied orbitals and one prediction for the empty orbitals. And you can see that in this case, this is an even more crude approximation than for the water system, because here in reality, the screening parameters cover a wide range of values between 0.2 and 0.4. And approximating this by a single value really also corresponds to huge errors in the orbital energies. We get even errors larger than 0.5 electron volts. So you can really completely forget about this model for predicting the screening parameters. Instead, if you use the more sophisticated machine learning approach, you get, again, already quite good results after only one training snapshot. So you can see that we are already able to recover this diagonal trend. And also the orbital energies are predicted more accurately than in a mean model. But still, I would say in this case, one training snapshot is not enough to have reliable predictions for the orbital energies, as you have many orbitals which have an error larger than 0.1 electron volt, and even some orbitals which have an error larger than 0.2 electron volts. So here I would say, or I would recommend to use more training data. But already after 3 or maybe 4 training snapshots, the predictions might be accurate enough for most applications. So you can see that we improve the prediction of the screening parameters, and correspondingly, we also improve the prediction of the orbital energies. We only have a few orbitals with an error larger than 0.1 electron volt, and we don't have any orbital with an error larger than 0.15 electron volt. And again, of course, this result improves as you add more and more training data. At the beginning, I said one of the goals of this project was to achieve a massive speed up. And just to show you for the 2 test systems, this is indeed what we see. So what I compare here are the times needed for the entire Koopmans calculation if we compute the screening parameters ab initio versus if we use the machine learning model to predict the screening parameters. And what you can see is that we get a 10-fold speed up in the prediction phase and a 70, nearly 80-fold speed up in the for the perovskite system. And this is really remarkable, I would say. So to conclude, what this project showed was that it is possible to accurately predict the screening parameters directly and only from the orbital densities. We also showed that already very few training data is sufficient to predict the orbital energies or predict the screening parameters to such accuracy that the orbital energies deviate less than 0.02 electron volts on average from the ones with the screening parameters computed ab initio. We saw that it is easily possible to get speedups of 80 times by using the machine learning model to predict the screening parameters instead of computing them ab initio. And since we think that this model is very useful in many applications, we started to integrate it into the Koopmans workflow, and it will be soon made available also in the official Koopmans version. And of course, we will continue to expand the functionality and include other models and also error estimation. Lastly, I would like to thank all my supervisors, as well as other people in the Theos group that helped me throughout the project and gave a lot of useful input. So thanks a lot, and I would like to take your questions now.
Thank you very much, Yannick, for this very nice and interesting presentation. So there is one question on Slack already. Can we relate the expanded total charge density Nmax equals to 6, Lmax equal to 6 to cluster model? So to say, only the most profound effects from the surroundings are captured?
I'm not really sure I know what you mean by cluster model. Maybe you can. I'm not very familiar with this expression.
Okay, no problem. Okay, there is another question from Nicola Colonna. Could you comment on the transferability of the model? How difficult would it be to predict screening coefficients for a system different than the one used for training?
Okay, so this is a very nice question. So indeed, what I showed was was a setup where we train the model more or less on a system that has the same atomic configuration, so the same stoichiometry and so on, and where simply the positions of the nuclei and correspondingly also the orbital densities change slightly. So in this case, I would say that the orbitals in the prediction phase are indeed quite similar to the, or at least the whole system in the training phase is indeed quite similar to the system in the prediction phase. And we will need further investigation to see how well we can transfer to other systems. What I can say here is that, as for Martin's talk yesterday, it is important that you don't change certain quantities like the pseudopotential or the dielectric constants, since this is not reflected by anything in the input vectors, and therefore the machine learning model would not be able to predict then the screening parameters accurately if you don't include them in the training data. So I would say in many applications we might need to modify this model a little bit to have more transferability. And yes, I think this is all what I can say to this at this stage, but yes, more studies are needed here to see.
Okay, thank you. There are no other questions. If they appear, you can answer maybe directly on Slack.
Sure.
But we thank you again for your talk, and also would like to thank Andrea Ferretti and Edward Linscott for their lectures this morning.